Hello, AP Stat students. When we first started Unit 6, we talked about confidence intervals and we did a one sample Z interval for proportions. Then we moved on to significance tests and we did one sample Z test for significance for proportions. Then we moved on to two samples. Last time we talked about a two sample Z interval for proportions. And finally, we will end this unit on doing a two sample Z test for proportions. The hardest part is writing a hypothesis. An observed difference between two sample proportions can reflect an actual difference in the parameters, or it may just be due to chance variation. In random sampling or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has the general form. So this is what the null hypothesis looks like. So the null hypothesis for a difference in the proportions looks something like this. P1 minus P2 equals this hypothesized value and that value is going to be 0 because you're going to assume that there is no difference. For now, we are going to restrict ourselves to situations in which the hypothesized difference is going to be 0. And in more advanced classes, you might have a difference of like 0.5 or whatever, but for our purposes, it's going to be 0. And so you can write it like this as well. So the null hypothesis states that P1 minus P2 is equal to 0. It means the same thing as what I wrote above. I'll write it here again. The alternative hypothesis says what kind of difference we expect. So if we're talking about two proportions, is proportion 1 less than proportion 2? Or is proportion 1 greater than proportion 2? Or is proportion 1 not equal to proportion 2? And it's really totally up to you on how you want to write it. This means the same thing. And then P1 minus P2 is greater than 0. And lastly, P1 minus, if you're just going to move everything to the left side, that should be not equal to, sorry. So let's do an example. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005 and 2006, 19.5% showed some hearing loss. Do these data give convincing evidence that the proportion of all teens with hearing loss has increased? So we are going to, in this particular example, state the hypotheses we are testing, define the parameters that we use. You have to define the parameters that you're using. And if you don't want to use like subscripts, number subscripts, you can use letter subscripts, which is what I'm going to use in this particular problem. So our null hypothesis states there is no difference. So the proportion of the earlier years is going to be equal to the proportion of the later years. So I'm going to call my 1988 to 1994 early years and the 2005 to 2006 my later years. And then our alternative hypothesis then would be that there's going to be an increase, and you want to write it so these match up. So if there's later years is going to be an increase, at the beginning you can write something like this. But then just switch it around so it looks the same. So the proportion in the earlier years is going to be less than the proportion in your later years. So this is the way I prefer. I don't like to put everything on the left side, where PE is the actual proportion of teens in 1988 to 1994 with hearing loss. And PL is the actual proportion of teens in 2005, 2006 with hearing loss. Oops. There you go. So that's the writing the null and alternative. Okay, for in this section, if the null hypothesis is true, so if P1 equals P2 is true, the two parameters are going to be the same. We call their common value P, but now we need a way to estimate P, so it makes sense to combine the data from the two samples. This pooled or combined sample proportion is given by the following information. So the combined sample proportion is equal to the count of successes in both samples combined and this is on your formula sheet under section 3. That's all we've done in this unit. When you look at your formula sheet, it's all under section 3. So the bottom of the first page and the top of the second page, divided by the count of the individuals in both samples combined. So this ends up being x1 plus x2 divided by n1 plus n2, where n1 and n2 are your sample sizes. Now you have a new standard deviation using the pooled proportion, and this is on your formula sheet, and this is what it looks like. So your new standard deviation of the difference in the proportions is equal to P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2, all under the square root. And now, since you have this pooled data, this is what happens. So you're using the combined information. So you have this P hat C times 1 minus P hat C over N1. And for the second sample, you have P hat C again times 1 minus P hat C over N2. And you can factor that out, and this is what is on your formula sheet. So you have P times 1 minus P times the square root of 1 over N1 plus 1 over N2. But you can just use this, which is what I prefer. Okay. So here's what the test looks like, the 4-step process. So in your state portion, you're going to state your hypotheses, test the hypothesis that the difference in the proportion of whatever and the proportion of whatever is 0 at whatever significance level. So you write your null and you write your alternative, just like that. And here's the different ways to write the alternative. Okay. Then in the plan section, you want to tell what test you're using. So you're going to use a 2-sample Z test for proportions. If the conditions are met, Then you'll do your 3 conditions. This is really important that you don't skip this step, because then you can't go and do any of the calculations. So is it random? This is stuff we've already done before. Check for normal conditions. You're going to have to check for, because there's 2 samples. And then independent, both the sample and groups themselves and the individual observations in each sample or group are independent, or the 2 populations are at least 10 times as large as the corresponding samples. You don't just call that it's reasonable to assume that there's 100 people. If that's the sample size, you would say 1,000 people. So don't forget to multiply by 10. Then in the do portion, you're going to compute the pooled sample proportion. So that would be P hat C is equal to x1 plus x2 divided by n1 plus n2. And this is on your formula sheet. This whole thing is on your formula sheet. And then to compute the Z statistic, so our Z statistic is equal to P1 hat minus P2 hat. And this is going to be 0. And it's going to be 0 because P1 is equal to P2. So you can just leave that part out in your formula. Because you're assuming there's no difference. Divided by the square root of that. So this is the standard deviation. So P hat C times 1 minus P hat C over N1 plus P hat C times 1 minus P hat C over N2, square root. Then you calculate the p-value by calculating the probability of getting a Z statistic this large or larger in the direction specified by the alternative hypothesis. Compare the p-value to the significance level which is alpha. If p-value is less than alpha, we will reject the null hypothesis. If the p-value is not less than alpha, we fail to reject the null hypothesis. So those are your only options. Interpret those results in context. So if we reject the null hypothesis, we will be favoring the alternative hypothesis. So we have convincing evidence of the alternative. If we fail to reject the null hypothesis, we do not have convincing evidence of the alternative hypothesis. And let's do an example. Let's going back to our teenagers going deaf. So we have, I don't need to reread this part for you. So we will go ahead and state our null and alternative though. So the probability, or I'm sorry, I don't know why I said probably. The proportion in the earlier years is equal to the proportion in the later years. And the alternative, the proportion in the earlier years will be less because the proportion in the greater years had more hearing loss. Where P1 equals, I'm going to just rewrite this. It's a good habit when you're doing a free response. So it's the actual proportion of teens 1998 to 1994 going deaf. And P2. Oh, we're not going to use P1, P2. We're going to change that to PE and PL just to be consistent on this one. But you can use 1 and 2. Just make sure you tell which is which. And PL is the actual proportion of teens 2005, 2006 going deaf. We will use a 2-sample z-test for proportions if the conditions are met. So random, simple random sample of 3,000 teens and a simple random sample of 1,800 teens. Okay, normal condition. So we have to do 4. So our sample size, 3,000 times, and I'll do 1988 to 1994 first, times 0.15 is equal to 450, which is greater than or equal to 10. And then we have 3,000 times 1 minus p, so 0.85. So the successes was 450. That equals 2,550, which is greater than or equal to 10. Okay. For the other group, the 2005-2006 group, we have 1,800 times 0.195. That happens to equal 351, which is greater than or equal to 10. And then we have 1,800 times 1 minus 0.195, so that's 0.805. And that gives us 1,449, which is also greater than or equal to 10. Okay, so the normal condition has been met. And for the independent condition, so I want to talk about why there's such a gap in the years. It's just because you really don't want the probability of one affecting the probability of the other. So there's that big gap, the 94 to 2005. So that takes care of some of the independence. And the other one, it's reasonable to assume that there are, so reasonable to assume that there are 30,000 teens from 1988 to 1994 and 18,000 teens in 2005-2006. All right, and now we can do our data. So for the combined proportion, that would be take your successes. So this value plus that value. So you have 450 plus 351 divided by the combined sample size, so 3,000 plus 1,800. And that'll give you your statistic. And that is 801 over 4,800, which is 0.167. Oops, that is our pooled proportion. There we go. And once we have that, we can calculate our z-score. So our z is equal to 0.15. So the proportion, the early years minus the later years, minus 0, so we just don't include that, divided by the standard deviation here. And it is of the pooled, so 0.167 times 1 minus 0.167, which happens to be 0.88 or 0.833 over sample size of the first, so 3,000, plus 0.167 times 0.833 over 1,800. You do all that. The numerator is negative 0.045. Be really careful when you're doing your stuff. And the denominator 0.011119992. And that gives me a z-score of negative 4.0468. Since it's negative, that is going to be your upper bound. So we want to then do our normal CDF. You don't compare this z-score to alpha. So you want to do a normal CDF. And our lower bound can be negative 100. Upper bound can be, or it has to be negative 4.0468. mean 0, standard deviation 1. Okay, and that gives you a p-value. So our p-value is going to be, it's going to be in, it'll show you 5.3 times 10 to the negative 6. So it's 0.000053. But that is definitely less than 0.05. So our p-value is less than our alpha. So we reject the null hypothesis. We do have convincing evidence that a higher proportion of teenagers in 2005 and 2006 have hearing loss than teenagers in 1988 to 1994. Part B. Between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, can we blame iPods for the increased hearing loss in teenagers? And the answer is no. I mean, yes, our p-value is low, but we don't blame that for the increase in hearing loss. We would truly need to run an experiment to show cause and effect. So no, we need to run an experiment to show cause and effect. And those are the complete notes for Unit 6. Have a great day, AP Stat students.